ring is so fast. Okay, so voltage of ring. So you're just going to basically argue, okay, if this is the radius and this is x, so you take a piece from there. Again, for voltage, you don't have to take a piece from here and here and say the fields cancel or anything. You just say, this creates a voltage there, and its dV is K dQ over R. And then you say, okay, let me integrate it over the whole thing. And then R is this distance, right? And then you just integrate the whole thing. And then since the distance is the same, the distance between the ring and there, remember this ring is coming out of the page. It's coming out of the page and going into the page like this. So this is supposed to be a 3D picture like this. So no matter where you're at, this distance R is staying the same, you see. So then when you integrate it, it ends up not being an integral at all. It's just KQ over the R is going to be square root of x squared plus R squared. Right? So the voltage of a ring is one of the quickest to calculate. So now if I want to check that answer, what can I do? I can negative differentiate that, and that should give me the general equation that we had for the electrical field of a ring. Right? So as a check, electric field of a ring should be negative dV dx, negative the derivative of that. So what is the derivative of a square root? 1 over square root function. The KQ, it should be negative, right? This could be written as x to the minus half. So remember, the negative half comes down, then you have x squared plus R squared to the negative 3 halves, right? Times the derivative of the inside, which is 2x. Okay, so then the negatives cancel, the 2's cancel, the electrical field of a ring. So then you have KQX over x squared plus R squared to the 3 halves. And I believe that was the equation, right? Because I remember when x was 0, the electrical field of a ring should be 0, right? So you could definitely see in this case it's advantageous to first calculate voltage, because it's so much even easier, even though this was also easy to calculate, but this one is even much easier. So then when you differentiate it, then you get this. So that technique of finding V first and negative differentiating it really is advantageous, especially in this case. So then you get the electrical field of a ring. Okay, now let's go to plates. Plate is a little bit more work, voltage of a plate, because then we have to integrate over a bunch of rings. Okay. Plates. Okay, so then let's do uniform charge plate. So then you take a ring, and this is X. You say the voltage created by that ring. What was the equation we just derived? KQ over square root of, so it becomes K dQ, where dQ is the charge of that one ring. You see? So K dQ over square root of x squared plus the radius of that particular ring. r squared. Okay. X squared plus r squared. Okay, so now then we're going to integrate that. So we're going to employ now this very same techniques that we did for electrical field. We're going to say dq is sigma dA, where sigma is the surface charge density, dq over dA. So then dq is going to be sigma dA right? And then if it's uniform, the sigma will come out of the integral. So then it'll be k sigma. If it's uniform, then the dA is going to be 2 pi r dr over square root of x squared plus r squared. And then the 2 pi will come out of the integral. So at this point, we could give this some dimensions again. So let's say the charge is again 10 nanocoulombs. Let's say x is 2 meters again. And let's say the radius is 1 meter again. Okay, so then, okay, so then k is 9 times 10 to the 9th. Q sigma will be what? Charge divided by the area of that plate, which is pi r squared, times 2 pi will come out of the integral. Then you have r dr square root of, then x is going to be 2, right? So then 4 plus r squared from 0 to the radius of the plate. Okay. Okay, so from r dr square root of 4 plus r squared, 0 to 1. Okay, so now let's put this into okay, so this one changes completely now. So x divided by 4 plus x squared to the power 0.5. X over 4 plus x squared, and then 0 to 1. Okay. Okay, so 0.23606, and then the pi cancels the pi. Okay, and then the Q was 10 nanocoulombs, so it's just going to be V 10 nanocoulombs. So then that's 9 times 10, that's 90, divided by R was 1 meter, so then that's just 1 squared. Where did this 2 come from? Oh, okay, 2 pi R. So it didn't come from doubling something. You just sometimes have to look to see in your steps where it's coming from. Okay, it's just a 2 pi r dr. Okay, so then it's that times this. Okay. So then basically you just multiply this 0.236 0.67977, right, times, just multiply by 180, right? Yeah, the pi's have already canceled. Okay. 42.5 volts. Okay, 42.5 volts. Okay, how about non-uniform? So again, that depends on if the charge, if there's more charge towards the ends or if there's more charge towards the center, right? So if we use the, let's see here, sigma is alpha. Let's say there's more charge towards the edges, alpha R. So the charge density is increasing linearly as you go out. So what would we expect? If there's more charge at the far edge, right? But the distance is farther away, right? So we would expect the voltage to drop slightly. So maybe 38 volts, something like that, versus 42. Okay. Okay, you guys do this now. Cool, get your feet wet a little bit. So first calculate what the alpha has to be, right? So that you can get the fudge factor. And then put this into there and then do the second integral. Let's see what you guys get. It should be a little bit smaller than the 42 volts.